Hello, everyone. David, Rachel, can you still hear me?
Yes.
Okay.
Yes, I can.
Thank you for joining us for today's webinar. We're excited to have you here today. The topic is RAM modeling with our Availability Workbench software. I'm Jeremy Henick. I'll be your host alongside David Wiseman. David will be showing us RAM models for today's presentation. David's very experienced in this topic. I think he's going on a couple decades. Is that right, David? Of handling the support and doing
Yeah,
training.
getting close.
So we're lucky to have him today. Before we get started, I wanted to talk about one thing with Isograph. I assume we have a lot of Isograph clients in here, maybe some Plato and IQS clients as well. Um, but recently, earlier this year, you probably received some emails about it. Unless, I guess if you're in this meeting, you're getting our emails. So Isograph has joined Peak Avenue. Peak Avenue is made up of three companies. One, of course, is Isograph, who specializes in reliability software products. That includes fault tree analysis and other safety products, reliability prediction, maintenance, availability, cybersecurity, and a few others. INS, formerly known as Plato, we have Plato up here. It's a web-based platform that includes it, but it's not limited to things like product development process, SysML, online FMEAs, control and inspection plans, things like that. And then the third company is called IQS, Quality Center. It includes things specific to QMS, which is Quality Management System, which is things like auditing, document management, complaints management, all part of the APQP process. If you're familiar with that acronym, it's Advanced Product Quality Planning. Um, the idea is we'll be taking all these software products and combining them in one integrated environment that allows these software products to share data. It'll be a true digital thread through the product development process. Um, if you're interested in discussing this more, please reach out. I always believe that our best future clients are our current clients. So if you want to know more about what's going on, please let me know. Here's the agenda. This is what you can expect today. I'll talk about analytical and simulations just a little bit, and then I'll hand it over to David, who will walk us through the RAM models he's created. We intend this meeting to be as interactive as possible. There's so many people on the meeting that everybody's muted. So if you have any questions, please post those questions to the chat menu, and we'll answer them there. Or we love complicated questions, but if we don't have time, we'll address all the questions later. And a recording of this meeting will be posted on our blog. Hopefully this week. I'm going on vacation tomorrow, but I'll try to get it up before we go. And then at the end of the meeting, we'll have a quick chat about our next meeting, where we'll be talking about how we model threat analysis. With that, let's get started. The Isograph is well known globally for our reliability workbench software, specifically our Fault Tree Plus software, since it's our oldest product. And we created that product before there was many tools out there to do these types of calculations. The nice thing about analytical methods is they calculate quick. You put in one number, you get one number out. It's an easy way of seeding if you're meeting your probability of failure goals, getting your cut sets, finding information like that out about your system. However, as your model matures, you start to realize there's some real world applications that become hard to create in the analytical models. Analytical methods don't really don't easily handle things like spares, rotating equipment, maintenance, capacity, throughput, things like that. When faced with those types of questions, you can move to simulation, which is what we're doing today. And by simulation, we're using a random number generator, which opens up a whole world of calculations. We use Monte Carlo simulation. There's a few others out there, like Latin Hypercube, maybe some others, but we prefer Monte Carlo simulation. If you're already a Reliability Workbench user, you could even take your existing models, your fault tree models, your RBD models, um, and move those structures into Availability Workbench along with all the applicable data. And then you can apply Monte Carlo simulation and start understanding what those calculations can do. David, if you're ready, I can just pass this over to you now.
Yeah, thank you very much, Jeremy. Yeah, so hi everybody. So no, not sharing the screen yet, but I will do in a couple of seconds. So yeah, thank you very much for that introduction, Jeremy. So today we're going to be taking a look at RAM modeling, specifically using simulation in the Availability Workbench. Now, I don't want to just jump straight into that. What I'd like to do is actually use more conventional methods as a point of comparison. Many of you might already be familiar with our Reliability Workbench software that uses things like RBD and fault tree to calculate reliability parameters, but doing so using probability, as Jeremy pointed out. And I want to use that as a jumping off point so that we can see then what simulation gives us on top of those older RAM modeling techniques. So now I will share my screen. I'll be careful to share the correct one. There we go. So on the screen right now, there are two windows that will look at first glance almost identical to one another. On the right is our Reliability Workbench software. On the left is our Availability Workbench software. Both of them have the exact same model built into them, as you can probably see from looking at them. They're both a simple block diagram. So you'll be familiar with the idea of redundancy. I've got three components. I've labeled them as pumps. In your imagination, you can think of them as anything you want, but I've just put pump because that's quite a familiar example for me. Three pumps in parallel. This system will be operational as long as at least one of these pumps is available. Only if all three were to fail would you end up with a system level failure. So I'm going to have a little look in the options to begin with, just to prove to you that they are pretty much set up the exact same way. So there is the lifetime of each system. So I've set the lifetime to each system to 10 years in both cases. And as you can see from the diagram, the pumps, each pump in each case, same information. The mean time to failure, 1 year, I've entered that in hours. Mean time to repair, 1 week in hours as well. So in most ways, well, in all ways, really, at the moment, the inputs for the two models are exactly the same. What's going to be different is the way the programs arrive at a result. So on the right, Reliability Workbench is going to use methods that actually you may be familiar with from fault tree. I've got the exact same model actually built in a fault tree in this same project. It would just be built as an AND gate. So those of you more familiar with fault trees, this is what that model would look like. Same input data again. And this block diagram is going to analyze that model in the same way as a fault tree would, come up with minimal cut sets and calculate the probability of failure. So it will work out the probability of failure for each block, and from that work out the overall probability that the system will fail. Just using probability theory, the sort of thing that we tend to learn in high school. What's the probability of event A and event B happening at the same time? What's the probability of event A or event B? Those basic probability theories. And it's really, really useful in a lot of applications and will give you a quick and efficient result about the probability, the frequency of a failure in a system. Where it can say falls short, but where the places where we can't really go with this method, let's say, is when we start to introduce more complex behavior. So think of things like dynamic failure rates, where maybe the failure rate changes with time, or the failure rate is different depending on the status of one component or another. For that, we need a numerical method, and Monte Carlo simulation, as performed by the AvSim in Availability Workbench, the one on the left, is what will give us that kind of power. It uses random sampling of statistical distributions to arrive at a result. Now, I'm not going to dive into the theory behind Monte Carlo simulation. That is a whole other webinar that even I'm not sure I want to give, but I'll talk a little bit about how that works as we go on. But these two models right now are fundamentally in their input, they are identical. So I can run my model of the system on the right, and it's going to give me, well, it's going to give me a number of parameters in the context of RAM modeling. So reliability, availability, maintainability. It might be most informative for us to actually have a look at the total downtime of that system, which is 0.58 it's coming up with approximately for this system. So in 10 years, we'd expect a little over 30 odd minutes of downtime from this system, which you might expect because it's not likely that all three pumps will be failed at the same time. Now, I'm going to keep that open, and I'm going to run my model on the left. Now, before I even do that, I might have another quick look in the options, and I'll show you this. This is the number of simulations I'm going to do. The number of simulations is instructing the program how many times to simulate the life of this system, this 10-year lifetime. I could simulate one lifetime, and the program might say, in that lifetime, you expect to see 27 minutes of downtime. But in the real world, I might, in the future, find that there was actually 50 minutes of downtime or only 15 minutes of downtime. How can I be certain that the result that I get from my simulated model is going to be accurate, that it's going to give me something that's representative of what I expect to see in the real world? Well, the way I do that is by telling the program to run through that system lifetime, not just once, but as many times as is really practical. And the program, I've instructed it to do it 1,000,000 times. And at the end, it's going to give me the average downtime that it observed throughout those 1,000,000 simulated lifetimes. Now, this is the only time I'm going to actually run a model during this webinar, because we might lose an awful lot of our lives waiting for it to finish. But I'll explain what's happening as it goes. So you can see at the bottom left, it's kind of ratcheting up the numbers. So what you're seeing there is not individual events happening. It's not individual failures or repairs. Each time that number goes up, that's how many lifetimes the program is simulated by that point. So you can see it's worked through almost 700,000 at this point. On the right is the estimated statistical error. Naturally, this is a statistical process, so there will be some uncertainty on the result, but the more simulations you can do, the less uncertainty you can expect. Now, we're going to hop over to systems in the results, and we're going to have a look, and you can see there, if I look at that, that's very, very similar, the two results within a percentage point or so. So you can see the difference between the two is negligible almost. It's within the statistical error, that difference that we're seeing. So I did see, if you bear with me for a moment. Yeah, okay. So we'll obviously look at questions at the end. I did see a question I thought might be helpful for the understanding of what's happening, but actually I think I misread it. But we will look at questions at the end. So yeah, the answers very similar, as we would expect, because the inputs are basically exactly the same. And we've done a lot of simulations to get the best statistics we can. But we wouldn't use a simulation for a model like this generally, just because it is so simple. As you can see, you can just as easily do it with a conventional block diagram, conventional probability theory. But let's kind of push it a little bit further. I'm going to close that, and I'm going to open up a slightly modified version of this model. Okay. So here's my updated version. Now, again, at first glance, it's going to look very similar. Same logic, same MTTF, same MTTR. What have I done to make this model go, let's say, a step further from what we were doing previously in the conventional block diagram on the right? Well, the change I've made is in the block properties itself. If I have a look in here, this last block, I've set it to cold standby. So you may be familiar with different forms of standby in a system: hot, warm, and cold. Hot standby is when a piece of equipment, when it's placed into standby, when it's not in operation, its failure and its aging behavior remain the same. It's as if it's operating all the time effectively. The other end of the scale, you have cold standby, whereby, again, if that piece of equipment is placed into standby, it does not fail and it does not age. It's effectively frozen, hence cold standby. And in the middle, you have warm standby, where the failure rate changes, but it's not zero. The failure rate might come down by a certain amount. So the piece of equipment is under less stress, so the failure rate is lower. And that's what I've done here. I've said pump 3, if it's not in use, will be in cold standby. So I'm not saying this will be in cold standby all the time. I'm saying if I'm not using it, it will be in cold standby. Which brings up the next question. How would the program know what, how would the program know when I'm actually planning to use this, pump? How does it know when pump 3 is going to be in standby? Well, this is achieved in this case using the maximum capacity. In AvSim, another thing you can do over and above what's possible in Reliability Workbench is to specify that each block has a maximum possible throughput, the maximum amount of system throughput that can be handled by that piece of equipment. And for each one of these pumps, I've said each one can handle 50%, meaning I would only need 2 of them to be operating in order to meet a 100% capacity target. Now, I can tweak what the target is, but by default, it's 100%. So wherever possible, the program will keep both of these blocks operational, and it will only use pump 3 if one of these 2 were to fail. Once it's repaired again, pump 3 goes back into standby, and I start using these 2 pumps again. So basically, pump 3 is a backup, and I only use it should one of the other pumps fail. I cannot do that in a regular RAM model like the one on the right. There's nothing in RWB that allows me to say that pump 3 cannot fail when I'm not using it. So let's take a look at the impact that that has on the final outcome. And again, make a little comparison. So again, there's our result from our conventional block diagram. Here is our downtime. Now, it's a little bit lower. I'm sort of spreading out the stress in a sense. I have one block that's a lot less likely to fail now, because if I'm not using it, it cannot fail. If it can't fail, it can't contribute to downtime. So by taking that cold standby into account, it's driving the downtime of the system down. Can't do that with a regular block diagram, as we discussed, but maybe at this point, we're not forced yet, not quite yet, to go into an AvSim model. Maybe there are other things in Reliability Workbench that can handle this kind of behavior. Now I'm going to ask you to brace yourselves, because what we're going to do next is have a look at a Markov model. There it is. Now, it looks a little bit like something that should be hanging on the wall of a modern art museum. what this is, if you've not seen one before, it's a Markov state transition diagram. Each state represents a possible configuration that the system can be in, and you can see them shown there. Things like A is working, B is working, C is in standby, and all the other possible combinations thereof. And then the arrows are the possible transitions between those states. They have rates that are equivalent to the mean time to failure and mean time to repair, lambda and mu, failure and repair. So I'm not, again, going to dig into that in a great deal of detail, other than to say this model, rather than using probability theory, is using some complicated integration methods to arrive at a result. So it's another numerical method, kind of like simulation, but taking an integration approach instead. So I could run that and look at the result. Now it's not going to give me, I think, a downtime, but what it will give me is an unavailability, which, if we have a look, is very similar to the mean unavailability that we're getting from the simulation. I think, again, with just about within error, within the standard deviation. So at this point, we've still not quite gone beyond what we can get from Reliability Workbench, but we're getting pretty close. Now, we might ask at this point, well, if Markov modeling can do what the simulation is doing, why are we not simply using Markov models? Which is a brave question if you've already seen this diagram. But think about this. Let's say it wasn't 3 pumps. Let's say it was 4 pumps instead. Now I have to have a state for every possible combination of 4 pumps instead of 3. I'm not going to try to calculate how many more states that is, but it is quite a few more. And you have to have all the transitions that are possible between those states as well. So as ugly as this is right now, it's going to get a lot bigger and a lot more complicated very quickly. Consider the RAM model, on the other hand, in Availability Workbench, the simulation model. All I have to do is add another block. It's as simple as that. So we could do it. We could probably do it with a Markov model, but it's going to get exponentially more complex as the system gets more complicated. And we're already looking at a pretty simple system as it is. So we're already hitting a point where maybe, AvSim, the availability simulation, is going to be really the only practical way to go. So that said, I'm going to expand that now. We're going to leave Reliability Workbench behind for the moment and stick with Availability Workbench. Okay, so we're using Monte Carlo simulation. We've already demonstrated, in small terms at least, how powerful that can be for modeling more complicated behaviors, for getting that more complex interaction between systems than what you would ordinarily get in, say, probability-based models like a conventional RBD or a fault tree. Let's take it a step further. I'm going to take up another model. This guy, you can see, is called rotation. So originally, I was saying that pump 3 was in standby, and I only used it if pump 1 or 2 were to fail. Crucially, though, if, say, pump 1 failed and I started using pump 3, once pump 1 was fixed, pump 3 would come back online. Pump 1 would come back online again. Pump 3 would drop into standby. So I'm always keeping pump 3 as my backup no matter what. In a real system, that might not be the case. It might be that when pump 1 fails, I start pump 3 up. Once pump 1 is repaired, instead of starting it up again, I put pump 1 into standby and carry on running with 2 and 3. I'm essentially rotating the redundancy each time there is a failure. I'm spreading the stress out between those 3 pumps. So in the output node in AvSim, in that second node in my block diagram, I can add what we call a rule. Now, there are a few different rules you can apply in a node. I'm going to choose one of the simpler ones for my illustration, rotate on out of service event, which tells the program to rotate the redundancy each time there is a failure. When a block fails and it's repaired, put that block into standby rather than putting pump 3 back into standby again. And that too can have a subtle impact on the result of our model. We find that the downtime has gone down a little bit again. You could argue that that's almost statistical. It's not a huge difference, but there is a drop there from about 0.4 hours down to about 0.37, just by spreading that stress out amongst those three blocks. So that's a fairly straightforward one. I will dwell for a moment on the concept of rules, though. I will be revisiting them in a later iteration of this model. But rules are one of the really powerful ideas in a simulated RAM model like this. It's one of the ways in which we can apply complex dependencies between objects in a model. So, like I said, telling the program that, if one piece of equipment, is failed, then that will become the new backup when we start it up again. We can also do things like change the failure rate of objects, change the MTTF of objects under different circumstances, change the maintenance behavior of objects. This is all a bit of a preview for stuff we're going to be seeing in a little while. But this idea of rules in AvSim is really important because it's going to let you model some of your system behavior in a great deal of detail, more so than you would ever be able to manage with conventional RBD and fault tree or even Markov. Because at this point, trying to do rotation in that Markov model, I did consider trying that. I did consider trying to come up with that model as a comparison point for this seminar. And then after about 10, 15 minutes, I decided actually that was a bad idea and deleted the model. So yeah, it gives you an idea of where the limits are with Markov modeling just because they can become so complex. So on we go. We're going to go to our next iteration of this model. And this one is really useful because those of you who have worked with fault trees in particular, and especially those of you who may have been on our fault tree training course in the past, one of the things we talk about is failure rates, specifically time varying failure rate. For anyone more familiar with mean time to failure, failure rate is just the reciprocal of mean time to failure, 1/. But it's a measure of basically how often a first time failure will occur in a component. So in a fault tree and a conventional RBD, we generally assume that the failure rate, that the mean time to failure, if you prefer, is constant. This is because of a limitation in the probability theory that we use. That time-dependent failure rate has no sort of arithmetic solution. There's no way to apply that in just a straightforward arithmetic probability calculation. So essentially, we have to assume that the failure rate is constant. Now, the underlying assumption when we say that is that we're doing maintenance. We are maintaining our system and keeping the failure rate constant in that way. So in a regular fault tree, in a regular RBD, we assume the failure rate is constant. There are limited ways of dealing with time-dependent failure rates, but again, they are limited. And ultimately, you'd only be using an average behavior in your model anyway, telling the program, okay, this is how quickly the failure rate changes, but the program can only work out an average behavior from that. What if you needed to model that in more detail? What if you needed to explicitly model wear out? This is especially important when you are making considerations for maintenance, the M part of that RAM model, the maintainability. If you need to model or you need to determine what's the best frequency with which to replace an asset, what's the best frequency with which to inspect an asset, things like wear out become very important, and you can't simply assume it's not there. Again, can't really do that with a regular model like RBD or fault tree. Here, though, in a simulation, we can simulate that wear out as if it's happening, almost as if it's happening in real time. So how do we do that? So people who have got an eagle eye might have spotted that actually this system has changed a little bit. It doesn't say MTTF anymore. It says ETA. Eta is the characteristic lifetime, basically an estimate of the life of a component before it fails, used for a viable distribution, a statistical distribution that is often used to describe time-dependent failure rates. I'm going to jump into my failure model here. This is the object that's giving all of these blocks their failure and maintenance behavior. So in there, instead of using an exponential distribution, which would give me a mean time to failure, I'm using, in this case, a biviable. So the biviable is it's actually two distributions. It's essentially two viable distributions stacked on top of each other. And again, I don't want to give you a kind of statistics lecture because I probably couldn't, but I will say, like I said, a viable distribution used to describe different failure rate behaviors. I've got two viables stacked on top of each other, one where the average life is 1 year, and I've got a shape parameter, beta, that's equal to 1. That indicates that the failure rate for this trend is constant. So throughout the life, random failures will occur with an average lifetime of 1 year. But I have a second distribution dropped on top of that. This one has a shorter lifetime, about 3 months. So this failure happens more often. And most importantly, it has a shape parameter of 2. Any shape parameter greater than 1 indicates that the failure rate is going up with time, things like wear out or fatigue. Then I've got a location parameter, gamma, that indicates when those failures begin. And that is set to about 6 months. So to explain what you're looking at here, I have a pump and it has random failures. It has a failure mode that is random and happens on average about every year. So an average random failure rate of about 1 failure per year. But after 6 months of operation, I might start to see wear out failures. Those come more often. The wear out failure rate is higher. And the wear out curve is about linear. So the failure rate of that wear out mode goes up linearly with time. Now there are other distributions you can use. Tri-viable would give you a full bathtub curve, if you're familiar with that concept. Burn-in, random failure, wear out. That could be modeled too. But in my model, I'm saying that I'm getting random failures every year, which is pretty much the same as what I had earlier, but I've added to that there are wear out failures that can start happening after 6 months, and that failure rate is a lot higher. So I've applied that for all of my blocks. I'm going to run my model. In fact, no, I'm not going to do that because I said I wouldn't. So I'm going to just look at the result instead. And we can see there, total downtime has gone up significantly. Earlier, we were looking at values at about 0.4. Now it's gone up to 1.4 hours. So there's quite a big increase in the downtime, as you would expect, because now I've got assets that aren't just failing randomly. They could wear out if I let them run for long enough. And that's something that can be important to consider in more complex RAM models. So just to kind of recap what we've done so far, because I am trying to tell you quite a lot in quite a short space of time. We've shown that, for a basic model, simulation, probability theory should give you about the same result. But with the simulated RAM model, you can start layering on more complex behavior, things like cold or warm standby, rotation of redundancies, and of course, wear out, things where the failure rate gradually goes up with time, or if you prefer, the mean time to failure goes down with time. And you can model the impact of that on your system. So on to our next model. We've considered wear out, and I said that wear out can be an important thing to consider when you're looking at working out what a maintenance strategy should be for a system. So I think that's going to be a good next stop. Maintenance strategies. In a regular RBD or a fault tree, you do have a limited capacity for dealing with a type of maintenance, specifically fault finding inspections. Those of you who've used our fault tree tool, for example, might have seen a a dormant failure model. It describes a failure that cannot be detected immediately. Instead, you have to inspect for that failure, and you can specify how often you do that inspection. That is really, besides going over to a Markov model, that really is the program's only concession to scheduled maintenance. It's pretty much as you can do where scheduled maintenance is concerned. But in AvSim, where we're doing Monte Carlo simulation, we have a lot more power to handle these more complex behaviors. So I'm going to go and open that model now. I'm going to open this one. Okay. So I've now applied a maintenance task to each one of these pumps. I'm going to open one of these failure models and take a look at the maintenance tab. Now, this is where my corrective maintenance is. This is my repair. So you've seen the MTTR in the diagram up to now. But I've also added a planned maintenance task. This is a proactive task, any kind of task that might improve the condition of the equipment in some way. So think of things like schedule replacement, lubrication, cleaning, things that will make the equipment better than it was before, push it down that failure rate curve. Now, that's not the only kind of maintenance that we're limited to. You can see there inspection is an option as well. For hidden failures, you can do fault finding inspections. But again, you can take it a step further because unlike the regular old RBD and fault tree, you can now do condition-based inspections as well. Specify that it's possible for an inspection to detect a problem before it results in a failure and tackle that problem before you get any unscheduled downtime. So I don't think there's time to go into all of that in detail. We can touch on it in questions if necessary. But I just want you to know there that you can have inspections and you can have condition-based maintenance as well. But let's look at the planned task that we've set up. It's only very simple. I'm going to say I'm doing this maintenance once every 6 months, which is a pretty sensible option, I think, in this model, because remember, I said that wear out starts to happen after 6 months. So maybe that's a good time to do that maintenance. I'll say that task takes about 3 hours. So I get about 3 hours of downtime if I do this maintenance. And I've applied that same maintenance task for all 3 pumps, which introduces a potential problem. I'm telling the program that I'm maintaining each of these pumps once every 6 months. Does that mean I'm shutting down my entire system for 3 hours to do that maintenance? Because that's going to drive up my downtime significantly if I do that beyond what failure is causing. Do I really want to do that? In some instances, people do it. There are plant shutdowns once a year, and you can model that, of course. But I might want to make it so that maintenance is suppressed in the event that another piece of equipment is already down. And that brings us back to this concept of rules. I've told the program that for pump 1, I am not going to do this task. I'm going to inhibit this task if pump 2 is down or pump 3 is down. So that maintenance cannot take place if either of the other 2 pumps is out of service. And I've applied the equivalent rules for the other 2 pumps as well. So 2 won't go down if 1 and 3 are out, or 1 or 3 is out of service. Similar for 3 as well. So I can tweak when those tasks take place. If I prefer, I can simply offset them. You might have noticed there's an offset option where I can just say, well, I'll offset them by a few hours from each other, or by 1 day or 1 week. So I'll do pump 1, and then a week later I'll do pump 2, and a week later I'll do pump 3. So there are different ways you can approach this. I've used the rules method. Just depends what is more appropriate for the system that you're modeling. Key thing is, each pump will be maintained every 6 months. I'm assuming that the pumps will be good as new after the maintenance. Doesn't have to be the case. You can specify a condition after maintenance if you wish that is not as good as new. Good as new, though, that might assume there's some kind of scheduled replacement taking place. So I will take a look at my results, and you can see that's actually pretty much dropped back to what it was before I introduced the wear out, which, if you think about it, does actually make sense. Because what I'm really doing by doing the maintenance on the 6-month mark, I'm telling the program to kind of cut off the wear out part of the curve. Wear out failures can't happen now. So it's a simplified example, but it does give you a good idea now, I think, of how the maintenance can impact the result. It's going to, certainly for systems that tend to wear out, introducing maintenance can have a big improvement in the overall availability of a system. So hand in hand with maintenance, you tend to find resources, most commonly people. The people who are doing the maintenance, the engineers, the technicians, the electricians, the drivers, everybody who's involved. Similarly, spares. Spares are a resource that get used up when you do maintenance or repairs in a system. And they can also have an impact on the availability of that system as well. Think about things like lead times, for example. System fails, it takes the engineer 30 minutes to get to the site of the failure, fix that problem. It takes 24 hours to requisition a spare for the repair. All of that adds up. All of it contributes to the downtime, contributes to the availability losses. It contributes to cost as well. This is something I've not even mentioned up to this point. You've probably noticed in one or two fields in some of the dialogues I've had up, that cost is an option. You can sort of deal with cost in a fault tree by having, say, an event tree linked to it with consequences that represent financial impact, but it's not going to be a detailed life cycle cost analysis, as you could do here by specifying how much your spares cost, how much the labor costs, how much the downtime costs, and see where all of those impacts are coming from. That's really a side story, though. We are looking primarily at availability for our model here. So I'm going to go on to my next version of this model, which is this one. Same model as the last version. So I've got those same maintenance tasks, those same rules that prevent them from happening at the same time. But now I want to specify what resources I need to do maintenance and repair. So on the left, you might have noticed I now have a spare and a labor category, spare pump and an engineer. Now I could spend another 15, 20 minutes talking about the different things you can do with this. I'm going to try and keep it simple. Obviously, you can include a spare pump and you can specify how much that costs. Should you need to, you can go into detail about storing that spare, how many spares you can store, what that costs, how long it takes to get the spare from storage. I mentioned lead times earlier. You can do everything all the way up to how long does it take to get a new spare from the supplier. And all of these things will have an impact. But again, I'm keeping my model quite simple, just a spare pump. I don't think I've set anything up for storage. No, I haven't. It's just that's how much it costs to buy a spare. I'm assuming that the spares are always there. It just costs money to buy one for the repair. I've also added this guy here, though, this engineer. If I open that up, we can see there I've got costs for that as well, if I wish. Have a corrective logistic delay, so that's how long it will take this person to arrive at the site of the repair when they're needed. No scheduled lead time, you'll notice. With scheduled maintenance, we assume, because it's scheduled, that the engineer will be there when needed. But I can say how many engineers I have. I'm saying I've got 2. This allows you to handle a level of maintenance queuing where maybe you don't have quite enough people to do all the maintenance. And if something fails while those guys are occupied, it has to wait until they're available again. How do I apply that? Let's use the model for pump 1 as an example again. Go to the maintenance tab, look at the corrective maintenance, where I've said I need 2 engineers and a spare pump to do that task. So I've said 2 people, that's going to be all my engineers, as it turns out, and a spare pump to perform that maintenance. I can also set that for my PM. In this instance, I've said for my planned task, for my scheduled maintenance, I only need 1 engineer. So I'll come out and do this task, whatever it is. And that isn't just for show. That isn't just so you can have a nice report that shows, okay, this is what I'm using for each task. When you run the analysis during the simulation, if one of these tasks takes place, it will draw on that, run those resources, and it will incur any costs and any additional downtime that is associated with those resources. And as we'll see, there will be an impact on the result because we've included that information. So I'm going to take a look at the results again. And well, now you can see I'm starting to get a little bit of life cost coming through as well from things like the labor and the spares. I'm going to ignore that for now. Take a look at the system where now I'm getting a lot more downtime. Before it was of the order of 1.4, something like that. Then it went down because I introduced the maintenance. Now it's gone all the way up again. Maybe you can already guess why that is. We've introduced a limited resource. We only have 2 engineers, and if there is a failure, we will be using both of them. And indeed, if there is scheduled maintenance going on and we're using 1 engineer and a failure occurs, one thing we can't do at the moment is say to the program, if there is a failure, down tools on any other task. It's not quite that sophisticated. There are always limits to what we can do a little bit, but it's going to get us very close. What we can do, tell the program we have limited resources, and that will have an effect. And the best place to look for that, well, there's a few places, but one place that's going to be useful, if we look at the failures of the individual components, because we've been focusing on the system itself, but we can look at each individual pump as well. We can see the downtime of each pump. And in this instance, crucially, we can see queuing time. We can see there that we are queuing for labor for up to about 50 hours in total. That's how much downtime we're losing from pumps 1, 2, and 3, waiting around for labor because it takes an hour for them to get there, or even because we don't have enough labor to cover all the tasks that are taking place. This can help us now to understand not just how we might improve the architecture of our system, but how we might improve our staffing levels. How many people do we really need to drive that downtime down further? We can even see that for spares as well. I've not introduced any queuing time information for spares, which is why it comes out at 0 for my example, but you can get that kind of information too. So we can see now that stepwise, we can layer more and more detail on, see where all of the failures, all the outages are coming from, not just failure and repair, but maintenance, resources, and other factors as well. So I think the last model I'm going to show you will bring into play something that is actually in RBD and fault tree, but again, not with quite the same amount of power. And that's phases. So let me bring up my last model. Phases. So if you've not come across this idea before, phases allow us to break the life or the mission of a system into different periods of time. So, I've got this 10-year lifetime that I talked about at the beginning. I could split that into summer and winter. I've created 2 phases. I've made it very simple. I've made each one 6 months, summer and winter, 6 months each. I could have more phases than that. I can even have concurrent sets of phases running at the same time. So if you wanted summer and winter, but also day and night, or also January, February, March, and so on, you could do that too. But we can break the system lifetime to different phases. In fault tree or in a regular RBD, that would allow you to change the failure rate of an event or a block based on which phase you're in, which is a very useful thing to be able to do. But here, we can actually completely change the way that different objects in our system behave based on which phase we're in at different times. So again, I'm using a simple example to show you how this works. Let's take a look at pump 1. So pump 1 hasn't changed from our previous example. It's still got its repair, its maintenance, its resources, its wear out curve. All that stuff is still there. But I've added a rule, yet another rule. And there are lots of rules you can apply for blocks, but I've chosen a fairly straightforward one. Set load factor during phase. Here, I've set the load factor to 1.2 in the winter. The load factor is a multiplying factor that adjusts the failure rate of the block. So what I'm saying here is, in the winter, the failure rate of this block, whatever it happens to be at the time, because of course it could wear out, it will be increased by 20%. So maybe during the winter, this pump is under more stress, maybe from freezing and other things, and the failure rate is higher. This is a very simple example of a rule that you could apply. So I put that in. I've done the same thing for all 3 pumps. We look at the results. There you can see the downtime has gone up substantially because now in half of the year, failures are a lot more frequent. We're off the failure rate of each pump is 20% more than it would be during the summer. So all these little details you can see can have a significant impact on the overall availability of a system. Now, this is really a cross section of what can be done with a RAM simulation. You can probably guess from looking at just the interface, there are a number of other things that are possible. I haven't talked about grouping maintenance tasks. I haven't talked about using failure history, which is really useful. I was entering my failure data by hand, but you could use real world failure history collected from a CMMS or an ERP system and feed that into your model to make the simulation more realistic. Great thing to be able to do. Not always easy because that information can be hard to come by, but it's an option as well. So just to round off what I've been saying, the RAM models that you can do with the Reliability Workbench are really useful. They can give you minimal cut sets, the combinations of faults that lead to a system level failure. And they can use probability theory to efficiently arrive at a result for things like reliability and failure frequency. But where they stop short is bringing in strong dependencies, things like dynamic failure rates, maintenance, complicated relationships between assets. You can do an element of that with Markov modeling, but it's limited by how complex a Markov model might become. So simulation gives you a way of quickly and efficiently building a complex model and getting a result out at the end using the Monte Carlo simulation method. And yeah, that is the end of my little bit about RAM modeling in AvSim with Monte Carlo simulation. So yes, I'll hand back to Jeremy, who I think is going to maybe read a few questions out before we close.
Yeah, that was a great presentation, David. Thank you. What, in your opinion, what would the limitations be? What are systems that you should consider before modeling in a software like AvSim?
Yeah, so I think the limitation is always statistics. So the comparison I always make is between, say, an oil and gas system. So oil and gas, very common users, tools like AvSim, and an aerospace system. 2 systems couldn't be more different. Because very often when you're talking about time between failure of sort of process systems, it can be often measured in thousands of hours. whereas components in an aircraft might be measured in millions of hours because they're very much more reliable as they need to be for an aircraft. That presents a problem for simulation because building the statistics required for an accurate result when something is only failing once every million hours can be very difficult. You'd have to do a huge number of simulations. It would take a very long time. This is why things like conventional RBD and fault tree, which handle probability calculations really well, they excel with high reliability systems like aerospace and automotive. Whereas simulation, where you're looking at maybe heavy equipment that needs maintaining and that might wear out, things like that, that's where the RAM modeling with simulation tends to excel.
Okay, thanks, David. One other question, when reliability workbench and availability workbench, why isn't there simply just an option to switch from Boolean algebra, for example, to Monte Carlo simulation?
Yeah, I mean, I think again, it's essentially the same argument. I think there are tools out there that kind of do that, that say, well, if I can't quickly and efficiently solve the probability calculation for my fault tree with a regular probability theory, use simulation instead as a shortcut. So I think there are places where you can do that. Again, the problem is if you're modeling an aerospace system and you've got things with failure rates 10 to the minus 7, 10 to the minus 8, getting the statistics required for an accurate result would be prohibitive. It would take a huge number of simulations to build up the stats needed. It's reliability workbench just doesn't do that because it's got better options for handling situations like that. Things like the Seri-Prashan approximation and the terms limit allow you to efficiently run huge models and get the results back quickly without needing to sort of resort to simulation. So it's, to use a British expression, horses for courses. It's RAM modeling with simulation. It works really well for those lower reliability systems, like I say, and then the probability theory is great for those high reliability systems.
Okay, thanks, David. And we have had a lot of really good questions. We will go through these questions and address each of them. I'll be posting this video on our blog, as well as responses to the questions. I won't put anyone's names in them, as well as an email will go out to you guys with these responses and a link to the blog as well. And just to move on to, can you see my screen, David?
Let me, yes, I can.
Okay. Just to, we just have a few minutes left. I just want to introduce the next webinar, which will be, we have a product called Attack Tree Plus, which when we developed it, we were probably ahead of the curve on threat analysis because this was 10, 15 years ago that we started working on Attack Tree Plus. Is that right, David?
I think Attack Tree Plus is actually significantly older than that.
Oh, okay.
We already had it when I started working here, which I don't want to talk about how long ago that was. But
Okay.
yeah, the one of the examples we provided with it was for breaking into a bank vault. There were no cybersecurity examples because almost wasn't a concern at the time.
Yeah. It is a mature piece of software, and its popularity is growing very quickly right now, for obvious reasons with cybersecurity. So our next webinar will be a threat analysis model. So Attack Tree Plus uses the fault tree analysis model as well, but applies things specific for threat analysis. We'll be using an automotive example, but it's a cybersecurity model, correct, David?
Yeah, that's right. Same concepts.
And I'll put the link to sign up for that webinar in the chat menu, and you can sign up ahead of time. These meetings have been quite popular, so if you want to sign up, just hold a spot in the meeting so that you don't get bumped out at the last minute. Then, of course, questions, we'll address the questions you have. If you have additional questions, please let us know. We're happy to answer your questions or have discussions, no matter how complicated, on what you're modeling or what your questions are. Feedback on the webinar, I would love it. Topics you'd like to see. I've gotten quite a few of these from our last meetings. My contact information is in the email that you would have received. It's on the screen now. And I want to thank you for attending today's webinar. I think it was really good. Thank you, David.
Thank you, Jeremy. Thank you, everybody, for coming. I look forward to answering all your questions.
Thanks. Okay, the meeting's in the menu. We'll be emailing out a link to the meeting as well.